welcome to the 19th lecture. So, similar to regular languages, there are context free, so there are limitations to the power of context free grammars, in the sense that there are languages that are not context free languages, and there is a pumping lemma, there is a version of the pumping lemma for context free languages that one can use to show that a language is not a context free language. Okay. So, today we are going to discuss the this pumping lemma for context free languages. So, the agenda for today is we will try to motivate the statement of the pumping lemma. Okay. So, before I describe the statement of the pumping lemma for context free languages, let us try to see how the proof goes, I mean how the statement actually comes through. Okay. So, let L be a context free language and G be a grammar for L. So, what can we say about a string W, or what can we say about the parse tree of a string? Okay. So, let W be a string in L of G and let T be the smallest parse tree of W with respect to G. Okay. So, when I say smallest parse tree, it is the parse tree which has the least number of nodes, and if you have a string for which there are multiple parse trees which have the least number of nodes, you can pick any one, it does not matter. Okay. So, take a grammar, take a string in the language of that grammar, and let T be the smallest parse tree of that string with respect to the grammar. Okay. So, what can we say about T? Okay. So, firstly, if so there are few things that we saw last time. So, suppose if we look at any path from the root to the leaf of a parse tree, it consists of variables. So, if the root has let us say k vertices, then there are k minus 1 variables, and the last node is either a terminal or epsilon. Okay. So, that is true for any path. So, if you have a path which has k vertices, then this is the property, and if the maximum degree of T is D and height of T is H. Okay. So, then actually what you can argue is that the number of leaf nodes is at most d to the power h, okay, because from the root I have d many children, at most d many children, and for each of those d many children I can have another d children. So, it is d square. So, finally, when I reach the leaves, it is at most d to the power h. Okay. So, if the maximum degree of T is d and height of T is h, then the cardinality of W is at most d to the power n, because W is nothing but the concatenation of all the leaves from left to right. Okay. Once again, we had seen this earlier. Okay. Now, consider the following. Okay. So, let us look at this tree. So, let us draw a picture. So, let us say that this is the tree that I have, this is my tree T, and let us look at a path in this tree from the root to a leaf node which has length at least h. Okay, so let us look at the longest path in this tree. We know that the longest path, so what can we say about the longest path? Okay. So if we take w as a string which has length greater than d to the power v plus 1, where v is the number of v is the set of variables, what do we have? So we already have that w is less than or equal to d to the power e. In addition, if we assume that w is greater than or equal to this, then what this implies is that the height of the tree is at least v plus 1. Okay. So this just follows from simple inequality. So let us take a path in this tree of height at least v plus 1, and let us look at the last v plus 1 vertices. Okay. So maybe this is a vertex, and I have this vertex, and if I look at this length, so let us say this length is greater than or equal to v plus 1. Okay. So if I look at the last v plus 1 edges, well, I do not want vertices exactly, I want edges. If I look at the last v plus 1 edges, this path will have at least v plus 2 vertices, and the last node of this tree can be a variable. Okay, it can it can be a terminal or it can be epsilon, but we know that all the other nodes of this path must be a variable. So this path has at least v plus 1 variables. Okay. So therefore, by pigeonhole principle, there exists a node there exists two nodes labeled with the same variable, okay, say r, in the last v plus 2 nodes. Okay. So let me draw this picture once again. So I have my tree, I have this path, okay, such that the entire path has length more than v plus 1. There must be a node over here which is labeled by a vertex r, and there is another node over here which is again labeled by a vertex r, such that this guy to this guy. Okay. So this entire path has length at most v plus 1 edges. Okay. So if I look at the last, so there will be something like this. So now let us consider the following subtrees. So I divide my tree into the following structure now. So I will look at the subtree that is rooted at this r. Okay. I will look at the subtree that is rooted at this r. Okay. So maybe this is some part over here, and I will look at the remainder of the tree. Okay, so the remainder of the tree is okay. Now let's give some names to these things. So whatever, so the concatenation of the strings on this leftmost piece, I will call this X. Concatenation of the strings over here, I will call this Y. Change this a little bit. So here I'll call this as U. I'll call this as V. The concatenation of these strings, I'll call this as X, Y, and Z. Okay. So my entire string was W. So this was a parse tree for W. So I can write W as a concatenation of 5 strings U, V, X, Y, Z, where X is the string that is being generated by the sub parse tree that is rooted at this bottom R. V, X, Y is the string that is being generated by the parse tree that is rooted at this top R. Okay. And U, V, X, Y, Z is the string W, okay, which is being generated by the root node. Okay. So what can we say about these pieces? Okay. Okay. So the first point is since I had taken this R to be, so of course when I look at the last V plus 1 edges where I have V plus 2 vertices, I can have many such pairs which get repeated. Let us say I look at the last such pair. Okay. So because I look at the last such pair, what I can say is that the height from this node to the leaf is at most V plus 1. Okay. So because the height is at most V plus 1, what I have is that the length of Vxy, whatever is being generated by this parse tree that is rooted at the top R, is at most the degree raised to the power V plus 1. What can we say about V and Y? Okay. So observe that both V and Y together, they cannot be empty, because if both V and Y are the empty strings, what I could have done is that I, instead of keeping this entire parse tree, I could have replaced the this parse tree rooted at the top R with the parse tree rooted at the bottom R. Okay. So if I give them some names, so let us say that this top parse tree is T1 and the bottom parse tree is T2. I could have replaced T1 with T2 and I would have got a smaller parse tree, because this length is the parse tree T2 is smaller than the parse tree T1. So I would have got a smaller parse tree which would have generated the same string W, because V and Y are empty. Okay. So therefore, both V and Y cannot be the empty string, as that would give us a smaller parse tree for W by replacing T1 with T2. Okay. Therefore, what I can say is that the length of Vy together is strictly greater than 0. Okay. Now, let us see what other strings are there in this language, what other strings I can generate using this parse tree. So if I look at this parse tree, suppose if I replace T1 with T2. Suppose if I do replace it, okay. So suppose if I look at this parse tree and now I replace T1 with T2. So I have T2 over here. So this part of my string was U, this part is X and this part is Z. Okay. So I get a string W, let's call it W0, which is equal to U, V to the power 0, V is absent, X, Y to the power 0, Y is also absent, Z, which is also in the language of the grammar, okay, because I have a parse tree with respect to the same grammar. If I look at another parse tree, okay, where I let's say replace T2 with T1, okay, suppose if I replace T2 with T1, this was my T2 earlier. So now I have U and this part is my T1 once again. So I have V and then once again I have V X Y and then once again I have Y and then I have Z. Okay. What is the string that I get? So I get a string, let's call it W2, which is nothing but U, sorry, this is V, V square, X, Y square, Z, which again belongs to L of G. Okay. So this was my vertex R, again this is also a vertex R, which is what I am doing. Okay. So now I very conveniently decided to do this replacement. Okay. So here I am doing this replacement, here also I am doing this replacement. Okay. But why is it that I am able to do this replacement? The reason why I am able to do this replacement is because both these nodes, okay, so both, if I go back to this parse tree, both these parse trees T1 and T2, they have the same root. So they have the same root R. Because they have the same root R or the same variable as their root nodes, therefore I could replace one tree with the other tree and get another parse tree which generates some other string in the same language. Okay. So that is a key point. So it is, we are using the fact that both these parse trees have the same variable as their root. Okay. So now I get a string W2 which is in L of G. Once more, so this is my W2. So inside this tree also there is a portion for T2. Okay. Okay, so I have this path. There is this vertex for T2. And once again, I can replace this T2 with T1. Okay, so what happens if I replace this T2 with T1? So what I get is so I have this, then I have this, and then I have a T1 over here with T2. Okay, so I have U. So what do I have? So I have U V. So U V, again V, then again I have V X Y, 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 and then z. Okay. So, I get another string, let us call it W3, which is u v cube x y cube z, once again which is in the language of the grammar. Okay. So, now we are in a position to state the pumping lemma. So, let L be a context free language, then there exists p greater than or equal to 0 such that for all w of length for all w such that length of w is greater than p, there exists a partition of w into 5 parts u, v, x, y, z, where v, x, y is at most p and Vy is greater than 0, such that for all I greater than or equal to 0, u v to the power I x y to the power I z belongs to L. Okay. So, the only thing that we have to fix is what is the p that we get. Okay. So, the p that we choose given a language L, given a context free language L in this case is so we set p equal to d to the power v plus 1. Okay. So, if I have a context free language, then there is a grammar for that context free language. So, given that grammar, I know what the number of variables in that grammar is, and I also know what the degree of any parse tree will be, the maximum degree. So, the maximum degree of any parse tree will be the maximum number of symbols that I have on the right hand side of any rule. Okay. So, that will decide what d is. So, I fix p accordingly. Now, if I take any string which has length more than d to the power v plus 1, then we have just shown that if I look at the parse tree of that string, if I look at the smallest parse tree of that string, I can partition it into u, v, x, y, z such that v, x, y is at most p. So, v is whatever is generated by the subtree T1 and vy is greater than 0 such that no matter what I greater than 0 I take, I can always construct a parse tree for that string, which implies that u v to the power I x y to the power I z is in the language. Okay. So, let me just make a note. So, note that p only depends on the context free grammar that we choose for L. Okay. So, since L is a context free language, there is some context free grammar for the language. Okay. So, what we will show next time is we will look at the contrapositive form of this pumping lemma, okay. So, which will essentially allow us to prove that a language is not context free. We will look at the contrapositive form. So, in the contrapositive form, if I take any language L, then for all p there will be a w with length more than p, such that if I take any partition with this property, there exists an I such that this string will not be in the language, and that would prove that the language is not context free. Okay. So, we will look at this next time, and also we will look at some examples of non context free languages. Okay. So, I will stop here today. Thank you.